I'm Luigi Pasquarelli. I used to be part of this team at the University of Geneva. Now I'm working at INGP. Things that I've been doing since the time in and I'm grateful to the two previous speakers because Mehdi introduced the theoretical framework that we are going to use in terms of forward modeling. So we do not perform inversion, but we are using the routine that Mehdi developed in a forward model. So try to simulate time series of gravity change, and thanks to Valentin, you know everything about lava fountaining at Etna. So basically we're trying to benchmark our model with the gravity change that has been measured in 2011 during the lava fountain. So basically the approach is the other. So we are trying to, instead of data-driven, as Valentin presented, we are building upon some simple physical modeling. What Mehdi presented, we are trying to build up scenarios. So try to have the simulation of time series, and then, as I said, it benchmark with the observation. We use past data because when I started this work, the instruments at Etna were not in place, so like UG just started to record. And as you know, the lava fountaining, I don't need to explain. I want only to point out that we are simulating lava fountaining for the NSEC now, a new Southeast crater, which is sitting here. This gravimeter, which is the EECPN that you already have heard during the morning, because it's a multi-parametric station on mountain. And we benchmark it with the data, and those are the data that also came out from the deliverable 4.2 that was done by Matthias and Daniele, where they took 7 episodes, were recorded episodes of gravity change during lava fountaining. They filtered them, they stacked them, they averaged them, and then we got this black line, which is our benchmark. That would be an average reference for a gravity change during the lava fountain episodes in 2011. And for this one, sort of arbitrarily, but also we took this part as our transient that we are going to use to benchmark our method too. And basically these 2 hours and a half of transient, they are pretty much also matching what in the visual camera at Mount Etna seems to be the beginning of the paroxysm. So it basically has to deal with the dynamic of the gas ascent, as Valentin also showed you, which is thought to be at the base of the feeding system of the lava fountaining. So basically, this is a short sketch. I go fast, but it seems that the increase of the content of the gas phase in the magma into the conduit up to very high level of gas content, they can be the thrust of the ascending magma and the trigger of the lava fountaining activity, and so the explosion of the paroxysm. What has been done by Daniele in 2015 and by other authors was just to focus on the gravity change induced by the magma chamber. What we try to improve here is also look at the conduit and what happened in the conduit using the previous developed routine. So, having this in mind, we basically developed 2 types of models. One, it's the one I'm presenting here. You have a magma chamber, which is an ellipsoidal one, which is connected throughout a valve with a cylindrical conduit. The cylindrical is rigid, so it doesn't give deformation, while the magma chamber has compressible magma that can be produce deformation. And the valve basically is setting up the time and the characteristic time of the magma ascent. So in the model is reported in the deliverable 4.5. I don't put equation here, but it's simply the idea behind is that the chamber and the conduit are hydraulically connected. So basically the change in pressure is coupled in the chamber, is coupled with the one in the conduit. So when you switch off the valve and you let the magma ascend to the pressure, you extract mass, and this mass will mirror the gravity change, as I can show you from this video. And basically with all the other parameters that are tweaked in the model, so low compressible magma, you can reproduce the time series of the magma chamber, which has always an exponential decay because the model is done this way. And then you have the conduit that is producing, in this case, an increase of gravity because of the mass accent, and the conduit was empty before. So that was, and then you have the contribution of the total chamber and conduit, which is the one to be benchmarked with the simulation, with the observation. We tweaked our model as best as we could with few parameters that you can play. Also the geometry matters a lot. It matters also the height of the gravimeter, but basically this is the best simulation that we could have, and we are able to match the peak to peak, or at least roughly to match, which is the amplitude of the gravity change, but it's very difficult to match the shape because the gravity is dominated by the mass lost at the chamber. This has an exponential function because of the pressure, so the mass follows the pressurization of the chamber, so we cannot really have different shapes. For the conduit, what we have to do is that we have to put a very high gas mass fraction, but what we want, because basically this is the physical explanation behind. And we have a positive contribution, but relative to the magma chamber, it's slower, so we can reproduce the peak to peak, but we have problem with the shape. And that's the drawback of this. Since we had this problem, we try to really instead solving only for the ascent of this magma bubble in the conduit. And for this case, we use the routine that made it. It's a rectangular tensile dislocation. So it's a 3D dike or whatever you want to see, that it's dynamically ascending, and the dynamics is set up from the mass eruption rate and from the time that we see the transient. And since the magma undergoes decompression, it expands the gas phase of the magma, and it's the opening of this tensile dislocation. It's increasing throughout the ascent, and you can have a very large opening. And these are the density profile that we get, assuming a simple decompression throughout the depth of the magma. And this is the porosity that we have at the end. For this case, since the model is super simple and very fast, we run Monte Carlo simulation, basically focusing only on the geometry, the starting depth of the tensile dislocation and the strike angle of the dislocation. So we run 10,000 Monte Carlo simulation, varying the depth in this range, and for all the 2 pi angle that can be of the strike. And we ended up with all this simulation. Those are the density profile, and those are the possible station height changes at the station APCN. And here, with a simple misfit criterion, we took the simulation that best has a minimum misfit compared to the observed data, which is the black line. And in this case, those are the best results of the best fit solution for us, which it's a depth of nearly sea level, so 2,900 meters below the crater top. And the strike is northwest-southeast, so 300 degrees from northeast. So basically, it's well oriented with the elongation of the crater that has been formed during the lava fountaining episodes, and also fits well the dike ascent at Mount Etna, so the local stress field. This one is the gravity and the best fit. Here we have a profile of density, which is not that bad in terms of density measured in the eruptive product. The only problem is that this model predicts a very large increase of the station height, so uplift at the station. So we get up to 20 centimeters in a 1 hour range, 1 hour and a half time. And these 20 centimeters, unfortunately, have never been seen at the Mount Etna. So I'm not sure whether there are high rate GPS inversion for no inversion, measurements for the station, but this seems a bit pretty high. So in this case, the model is perfect. I don't know, it's pretty astonishing for me. So it does a good job, but it predicts more deformation. And this is the results is also because here we have the profile of the total gravity change before, and you can see here, without caring about all the curves, that here the total minus the free air effect is the one which is dominating. So basically, the uplift of the station is giving us most of this decrease in the gravity. So I presented these two models in order to be fast, and we developed this model. They have pros and cons. We are not maybe the best to describe the lava fountaining processes and the gravity change, but they are easy to implement, fast, and they can apply it to any type of volcano. So maybe they are not useful for this particular application at Etna, but they can be extended to other cases. And the main problem is that with chamber plus conduit, we can not reproduce the shape. With the other one, it gives us larger deformation that it has to be seen whether, it has been recorded or not in this situation on Mount Etna. But the only point that we were discussing also yesterday, here we are dealing with models and benchmarking with 1 point and 1 time series that we have. The ideal would be to have a network, distributed network of high resolution deformation and gravity that will allow us to put more constraint in space and time and see whether this model can be discarded or not.